Hello, good morning again. Uh, uh, Thanks for joining the Vitals webinar on Introduction to CFD and CFD software, STAR-CCM Plus. We'll keep, if you have any questions, there is a question and a tab is at the bottom of the screen. So, please put your questions there. At the end of the webinar, we will go through the questions. So I think we can start. So the agenda for this webinar is we'll go through the company overview, Vitals overview, the core capabilities of Vitals PLM, and then we'll jump onto what CFD, advantages, limitations of CFD, what's a CFD process, typical CFD process is, and introduction to STAR-CCM, its capabilities and where it's used. And at the end, we'll showcase some case studies with multiphysics applications. Overview, Vitals PLM is based in Houston. Vitals is a Siemens PLM partner providing software solutions, training and consulting services. We have offices in Houston and other major cities like Detroit, Chicago, Cincinnati, San Francisco. We provide like engineering and we have an engineering and sales team with extensive cross-industry experience with advanced degrees. We are a solution partner for PLM for STAR-CCM Plus, NX Nastran, FEMAP, Nastran. So if you have any interest in knowing more about these softwares, you can contact us. Our team consists of PhD and masters in solid mechanics, fluid mechanics, materials, corrosion, data analytics, and optimization. We provide design, engineering, and data analytics consultancy, automation, and customization too. The next few slides are about our engineering capabilities. We can help with detailed component design, FEA-based fracture damage mechanics, reliability-based design optimization, multiphysics, CFD simulations, thermal analysis, structural reliability and risk assessment, composite designs and analysis, fatigue analysis, automation, and advanced equipment installation analysis. Coming to the FEA, we can help you with component design by analysis, FEA-based fracture damage mechanics, optimization and reliability, composites and elastomer modeling, flexible pipe and umbilical cross-section, structural analysis, integrity management, fitness for service, root cause analysis, geotechnics, vibration, and fluid structure interaction. Coming to our safety capabilities, we can do, we can help you with combustion modeling, fluid structure interaction, aeroacoustics, acoustic source modeling, blast and explosion, erosion modeling, chemical reactions, vibrations, mixing, and heat transfer. So let's start our main topic here, the computational fluid dynamics. So before going into fluid, what is CFD? Let's see what is fluid dynamics. Fluid dynamics is a field of science which studies the physical laws governing the fluid flows under flow conditions. The main three governing equations are conservation of mass, conservation of momentum, and energy. So conservation of mass can be neither created nor destroyed, and the conservation of momentum is conservation of momentum. It states the time rate of change of momentum is equivalent to the sum of forces acting on an infinitesimal fixed control volume. And the conservation of energy, energy can neither be created nor destroyed. So in fluid dynamics, we'll be solving these three equations to get to a solution. What is computational fluid dynamics? It's a branch of fluid mechanics that uses the numerical methods and algorithms to solve and analyze problems that involve fluid flow and heat transfer. So where is this used? It's used it can be used in conceptual designs, detailed product development, troubleshooting, redesign of an existing product. So CFD has been successfully applied in many areas, including automotive, oil and gas, sports, marine applications, aerodynamics, mixing, electronic cooling, chemical, and environment. So advantages of CFD. CFD gives a comprehensive information. It gives for the necessary engineering data to guide the design process. Experiments only permit data to be extracted at a limited number of locations in the system, but whereas CFD, it gives a large number of, you can monitor at large number of locations in the region of interest, and it's a comprehensive set of flow parameters for examination. It's relatively low cost compared to testing. Physical experiments and building prototypes can be very expensive, and CFD simulations are relatively inexpensive, and it can reduce time to meet market with automated design process. And using CFD, you can actually simulate the real conditions. Many flow and heat transfer process cannot be easily tested. Like the picture you see here, if there is a blast or explosion, it's easy to replicate that and do the testing. So CFD is a very helpful tool here, where you can actually model the real scenarios, and CFD provides the ability to theoretically simulate any physical conditions. Coming to the limitations, physical models. The CFD solution can only be as accurate as the physical models of real world process. Like, it depends on which turbulence model you choose, the compressibility, is it an ideal gas, is it real gas, the chemistry, how do you model multiphase. So it all depends on the physical model you use. And a strong engineering knowledge and knowing best practices could help minimizing this modeling errors. Numerical errors, because we are solving a bunch of equations here, there will be invariably there will be some numerical errors in the model. Boundary conditions, the accuracy of the CFD solution is only as good as the initial and boundary conditions provided to the numerical model. And the validation of the results with test data is really helpful to overcome these limitations, and also helps in building confidence in the numerical model. A typical CFD process, it starts with formulating the problem, like what's the main objective of the analysis. So what's the best way to obtain the objectives, identifying the flow domain, operating conditions, whether you can simplify the problem as a study problem. Can you solve it as a study problem, or is it laminar, turbulent? Are there any reactions? Is there a multi-phase flow? So we have to formulate the problem before jumping onto the modeling. Typical CFD process includes, once we formulate the problem statement, it starts with geometry modeling, mesh generation, identifying the physics, whether it's single phase, multi-phase, turbulent, laminar, non-Newtonian, Newtonian, combustion, and then the initial and boundary conditions. What are the boundary conditions on our fluid domain, and solve the equations, the Navier-Stokes equations, or the equations, and do the analysis, validate the model. This is really important. Once we validate the model, then we can actually automate the process to improve the design cycle. STAR-CCM Plus. STAR-CCM is part of Siemens SimCenter portfolio now. Here we'll introduce overview capabilities, but most of the topics will be discussed in upcoming webinars in more detail. STAR-CCM is a part of a SimCenter portfolio now. It's a comprehensive suite of simulation software and test solutions that helps companies address engineering challenges of today's complex products. SimCenter combines simulation and physical testing with intelligent reporting and data analytics to produce digital twins that more accurately predict product performance and drive innovation throughout all stages of the product development process. So it can be used for innovative designs with multidisciplinary design exploration and data analytics. So this is where the STAR-CCM sits in the SimCenter portfolio. STAR-CCM is a multi-physics simulation leveraged with design exploration. It's a CAE solution for solving multidisciplinary problems in both fluids and solid continuum mechanics within a single integrated user interface. The STAR-CCM simulation environment offers all stages required for carrying out engineering analysis, including geometry, development, mesh generation, solving the governing equations, data analysis, automation, and co-simulations. STAR-CCM, the geometry, we can directly input the geometry from native formats like CATIA, Siemens, NX, SolidWorks, Autodesk, Inventor. We can also import neutral formats like IGS, STEP, Parasolid, JT Open, and also the triangulated formats and PLM formats. We can use CAD clients, STAR-CCM add-ons embedded within leading CAD systems, CATIA, SolidWorks, where you can directly import and export the geometry from let's say here, the NX CATIA to STAR-CCM and STAR-CCM back to the CATIA. And in STAR-CCM, we can also create and modify the geometries. As you can see here, you can create a spiral tube, and then the whole geometry here is built in STAR-CCM Plus. So you can build some complicated geometries in STAR-CCM Plus itself. And we can easily extract the fluid domains and also copy and paste around the multiple bodies. Mesh framework. STAR-CCM provides a complete set of capabilities for both surface and volume meshing operations. Conformal polyhedral and tetrahedral meshes across multi-part assemblies, local mesh modifications, sequencing and reordering of mesh operations. Here, as you can see here, the mesh size varies with the solution. Surface meshing, you can prepare the surface for volume meshing, and then there is an option for surface wrapper. If you have a complicated geometry, you can wrap the surfaces easily and get a closed volume. You can do surface remesher and also 2D measures. Volume meshing, core measures, trimmer, polyhedral, tetrahedral, and prism layers. Here you can see the poly mesh, it's multi-phased, trimmer, and then triangulated tetrahedral. We have a specialized measures like a thin part measure that can be used for thin surfaces. Like say if you're modeling a conjugate heat transfer, including solids, you can use the thin measure for to mesh these kind of thin faces. And a cylindrical measure, you can actually mesh on a single face and extrude that mesh or a cylinder to minimize the mesh count. the extruder mesh, and offset measure. Directed measure used for sweeping mesh from one phase to the entire region. For physics, we can solve inviscid flows, laminar and turbulent. We can solve incompressible, compressible, multi-phase mixtures, Newtonian and non-Newtonian, porous resistance, study and unstudy, both explicit and implicit. For the gas equation of state, to model gas, we can specify constant density. We can use ideal gas law or real gas laws or polynomial density, or you can specify your own equation of state. And for materials, STAR-CCM comes with a huge database with for different materials in all the three phases like solid, liquid, and gas, and some electrochemical species too. And we can add or modify user-defined materials and properties. XML format allows direct creation of user-defined database. So you can also create your own database using in STAR-CCM+. STAR-CCM can simulate all modes of heat transfer in both fluids and solid materials, conduction, convection, radiation. In radiation, we have a surface-to-surface model, solar loads, and discrete ordinate model if there is a if the fluid absorbs heat. For the turbulence, these topics are a separate webinar topics on its own. Here we briefly touch this to show STAR-CCM capabilities. Turbulence is a detailed study in itself, so as we said, like we'll discuss it later. STAR-CCM includes a range of industrially relevant turbulence models for modeling different flow behaviors, allowing an appropriate balance between runtime, robustness, and accuracy to be achieved. We have multiple Reynolds average Navier-Stokes like Spallet-Almaraz, K epsilon, K omega, Reynolds stress transport, and to model flows between in the transition region that's not laminar, not turbulent. So we have turbulent suppression, gamma ray theta models, and gamma models. And it also comes with large eddy simulations and detached eddy simulations. A detached eddy simulation is a hybrid LES-RANS approach that solves turbulent structures in the core flow and covers the wall boundary layers by a RANS model. So this is least expensive. I mean, it's less expensive than compared to the large eddy simulation models. Multi-phase flows, we can use Eulerian approach or Eulerian-Lagrangian approach. For Eulerian, we have Eulerian multi-phase segregated flow, volume of fluid film models, dispersed multi-phase, mixer multi-phase. For Lagrangian, we have Lagrangian multi-phase and the discrete element method. So the first EMP model is can be used for modeling miscible fluids mixed on both length scales smaller than we wish to resolve. VOF, volume of fluid approach, is used to track the motion of free surface for immiscible fluids. Fluid film model is used for modeling a thin layer of fluid on surfaces. And dispersed multi-phase model simulates dispersed phases in an Eulerian manner. This is similar to the Lagrangian multi-phase. Mixed multi-phase is used for similar applications to EMP, and phases are assumed to be miscible here. For the Lagrangian, here we discrete rather than the continuous phases. This is suitable for dilute dispersed phases. Discrete element method is an extension of the Lagrangian framework that's suited for dilute discrete phases where particle shapes and collisions are important. Coming to the physics, The motion specifications. User-defined rigid body motion. We can specify the our own rigid body motion, how you want to model the motion. Dynamic fluid body interaction with all 6 degrees of freedom. We can superimpose different motions. There are body couplings, as you can see here, two boards connected to each other. So we can use these couplings, any external forces acting on the structures, and then the contact prevention between the surfaces. Moving mesh techniques, we have a sliding interface, overset. It's also called chimera mesh. Moving reference frame, MRF, mesh morphing, blade flutters, and user-defined motion. For the reacting flows, we have multiple different models like flamelet model, reacting species transport, and additional models to model emissions, 1D reacting channels, and surface chemistry. STAR-CCM provides an integral finite element solver for the solution of solid mechanics, fluid structure interaction, and thermal stress problems. Here we can solve static, dynamic, and quasi-static analysis, linear and non-linear geometries, 3D linear and quadratic solid elements like hexahedra, tetrahedra, wedge, and pyramid-shaped cells elements, isotropic, orthotropic, and anisotropic elastic materials, Rayleigh damping, loads and constraints on points and surfaces, thermal stress from mapped temperature field, bone and small sliding frictionless contacts, and one-way and two-way FSI. Here we can see the propeller moving, that's modeled within STAR-CCM. Here you can see the fluid, and then the fluid model, and on the right the structural model where the pressures, forces are mapped onto the structural model. Coming to the solvers, it comes with both single and double precision. It's a finite volume method, solving segregated and coupled flow solvers, simple and piezo solution algorithms, algebraic multi-grid linear solver, multiple discretization schemes for convection and for time. Finite element method, it's shared or distributed memory linear direct solvers, in-core or out-of-core memory storage, memory estimation, and multi-threading. We can use parallel execution. As you can see here, up to 60,000 cores, we have a very good parallel capability. For data analysis, we can generate multiple reports like system reports, statistical reports, and reports specific to some selected physical models like emotion or chemical reactions or something. And we can monitor these reports using monitors, and we can write your own field monitors. Plots, you can generate XY plots, histogram plots, and monitor plots. For visualization, you can visualize different geometries, mesh, scalar, vectors, streamlines, and also you can animate them within STAR-CCM Plus itself. Simulation summary. Simulation summaries, we can export the summary of your simulation in an HTML format for the details, and the solution history, it stores chosen simulation data on specific analysis surfaces. There's a star view. This is a license-free scene viewer for 3-dimensional STAR-CCM Plus scene files. And in the latest version, it comes with STAR-CCM Plus VR. It's you don't need a license for that. For virtual reality client for STAR-CCM that provides exploration of simulation results. Design exploration. This is also another topic for a webinar, but here we just touch base here. So within STAR-CCM, you can it provides an automated approach for running design exploration studies. It comes with performance assessment and design optimization models, where in the performance assessment you can specify the manual studies, like you want to change this diameter or some parameter, and also you can do a design sweeps. You can specify a range, and STAR-CCM will do automatically do the multiple analysis at different variables. And for the design optimization, it has an optimization cycle, design of experiments, and stochastic analysis. And for the design exploration, we can do co-simulations between STAR-CCM Plus and 1D tools like GT Suite, LMS Imagine Lab, AimSim, Relab, Wave. You can do co-simulations between STAR-CCM Plus and 3D tools like Abacus, and third-party by user-specific tools using co-simulation API. We can also do file-based coupling between STAR-CCM Plus and CAE tools. Abacus using input files, ANSYS CDB files, Nastran files, and Cyther. We can also use data mappers like surface to surface, or surface to volume, or volume to surface, or volume to volume, or you can directly import a table boundary conditions, and then you can use a table to talk between two different softwares. Usability and productivity. You can customize simulation trees. You can easily compare simulation trees, simulation tree comparison. Like, say, if you have two different simulations, you want to know the differences, you can simply go into the file, compare simulation, and then you can easily compare two simulations and see where the differences are. And you can write your own field functions. You can define your own parameters, filters, and tagging. Coming to the support, it has a huge database for documentation. There's a Steve portal website. Here you can see where you can have documentation. There's an idea storm, and you can and there's so many knowledge-based questions, and a dedicated support. You'll have a support engineer assigned to you. You can directly work with them if you have any questions. Coming to the applications in various industries, aerospace, you can use it for passenger comfort. Drones, combustion modeling, turbines, and the film cooling on CHD of a jet engine, turbine blades, etc. This is done using overset mesh here, and then this is a combustion. Here you can see the drone to do the lift and drag coefficients. In automotive, heavy industry lifting, like different solid materials, sunroof aerodynamic shape, flow around the car, and water management on the exterior of the vessel. And coming to the marine applications, this is a fluid structure interaction where here you can see the structural deformation on the hull. So you can directly integrate FEA in flexible vessels, marine propulsion, generation of waves. Here we have superimposed 180 linear waves to generate this nonlinear wave behavior. Oil and gas, we can do sloshing in a separation equipment on a floating production facility here. You can see that. And then drilling, flow and temperature through heat exchangers, sand transport, erosion, etc. Electronic cooling, we can do natural convection, natural convection on an electric setup box, and then the electronics thermal management. This is a design exploration study for thermal analysis on the motherboard. Other industries include, appliance industry, medical industry, etc. Okay. Here I have a couple of examples, couple of case studies on the FSA applications. Here you can see it's a fluid structure interaction wave slamming on an offshore platform. Here CFD and FEA coupled analysis on fluid flow and structural deformation on floating platform. A wave slamming on rigid wall by breaking waves and water bullet. Here we studied the rigid and elastic structures during wave slamming conditions. So the key interests are wave impacts are very sensitive to shape of incident waves, and handling different types of wave types, air entrainment, air entrapment, and accounting hydroelastic effects, and imposing spatial phase variation between hull and wave makes the study more complex. Here, this is an extension of the previous slide. This is on the structural side. Here you can see the geometry and the sensor locations and the computational domain. So it's modeling of integrated fluid and structural domain, scaling the model for computation simplicity, modeling for of sensor systems, structured meshing. It's piping flow induced motion. Here, because of the flow pulsation, flow variation inside the pipe, here you can see the deformation, and you can monitor the displacements on this pipe structure. So we came to the last slide here. So our value proposition here is, we prompt and complete technical solutions for your consulting projects. We look for a long-term commitment towards technology partnership. We're CFD and FEA experts with knowledge of industry applications. We have rich technical consulting experience background. We'll do knowledge transfer through training services, and we can do local support. Thank you. Let's see if you have any questions. Okay. We have a couple of questions here. So the first one is how to choose a base size while meshing. For that, the base size generally, select the smallest gap in the geometry. So the base size that we use is the smallest gap in the geometry. And then does STAR-CCM Plus integrate with SolidWorks too? Yes, we have a SolidWorks CAE Yes, we can directly use, we can link STAR-CCM Plus and SolidWorks for our CAD modifications and simulations. They can talk to each other. What is the cost? I think a sales representative will, will get in touch with you to know the cost. I'm assuming that's the cost to integrate the STAR-CCM Plus and SolidWorks. So for that specific cost, we'll get back to you. Is FEA solver NX Nastran? I did not understand that question. Could you elaborate on that? Is the software sold in modules, a CFD and structures, etc.? No, it's a comprehensive software. You can do both CFD and structural analysis together in the same. It includes in the same module. Is it Siemens FEA? Yes, NX Nastran is Siemens structural software. So we can help you if you need any help with NX Nastran. And how can I get a conformal mesh with different regions? If you use a polyhedral mesh, you can get a conformal mesh. Hexahedral, sometimes it's hard to get a conformal mesh on the using trimmer. What training classes are offered? It's introduction to STAR-CCM Plus, any software that's offered by Siemens or any other software. One of us will get back to you on that. What is the size limits for the far field boundary for the aircraft simulation? It seems like the limit is 500 meters. If I use a circle as far field boundary, is it right? I don't think there is a limitation on the size that you can create at the 500 meters, but I can get back to you on that. So I don't think there is a size limit. I'll get back to you on that. Is optimization program inbuilt to STAR or separate software? We can do manual sweeps and manual and design sweeps within STAR-CCM Plus. There is no additional cost. But for design optimization, there's a separate module for STAR-CCM for the design optimization. Some software has license that only allows specific applications like CFD for a specific flow, then another license to include other flow models. Now, STAR-CCM Plus has everything is in one module where you can do different flow problems, including combustion, multiphase. Everything is in one module. You cannot separate them. So if you buy the software, you can do multiple multiphysics models. So there is no you don't have to buy another license. Does STAR-CCM Plus include FEM model? What model is used in STAR-CCM Plus? Yes, it has an inbuilt structural model. within STAR-CCM. It's STAR-CCM plus structural model. For pre-post processing turbo machine domains, compressors, turbines, rotors, can we generate data in cylindrical coordinate system? For example, surface of revolutions, blade to blade. Yes, we can do. We can create different coordinate systems for geometry modifications or to specify boundaries or even for post processing. You can do that. You can create your own cylindrical, spherical, Cartesian coordinate system within STAR-CCM+. So how to speed up the temperature field convergence in conjugate heat transfer problems? If you're modeling conjugate heat transfer, to speed up the simulations, you can increase the energy solid under relaxation factor from default 0.9 to some 0.999 or something. So it will speed up the process. Is there a free student software that students can use for their projects? I'm not sure about that. I don't think there is a free student software, but I can get back to you on that. So then I think that's our last question. So let's wait for another 2 minutes and then we can wrap up the webinar. Okay, thank you so much for joining the webinar. If you have any questions, you can contact us. You can email to this email address, Ayman A. So talk to you in the next webinar. See you. Bye. Oh, there is one more question here. Can you speak to the learning curve steepness to get familiar with the software? It depends. I mean, it's pretty straightforward. It depends on what type of examples, what kind of problem you're trying to solve. If the simple pipe flow, you can do it. You can learn it in a day. But it depends on the physics, your background. So if you have experience in other CFD softwares, it's pretty similar. If it's something new, like a new software, if you're coming from a different background, I think a week training will help you to speed up the, to improve the setting up the models. And of course, we can help you with training. What programming languages communicate with STAR-CCM? You can write Java code, and STAR-CCM plus is based on C++, but for user defined, you can use Java. Okay, I think that's our last question. So thank you for joining. Talk to you next time. Bye.